Let's talk about linear functions. So section 1.3. With linear functions, we are going to learn how to identify if something is linear, find the intercepts and slopes of the graphs of linear functions, graph a linear function. We're also going to find what we call the rate of change of linears, identify the constant functions or identity functions, and then we're also going to look at some of our applications of it, looking at linear revenue, cost, and profit functions, and find marginal revenue and marginal profit. Okay, so let's start with our definition of a linear function. A linear function is a function that can be written in the form f of x equals ax plus b. Now, as we take a nice, pretty look at this, remind yourself that basically a and b are going to be a constant number. Now, this is the definition of what it means to be a function. You may be a little bit more familiar with this in the way that you may have seen it with y equals ax plus b. Just remember that when we talk about f of x here, f of x and y are actually the same thing. Now, when I look at this, it could be written as, say, 2x minus 5. It could be written as 1/2 x plus 7. It could even be written with that f of x notation and be like -5/4 x plus the square root of 3. Okay, all of these are different ways. And again, basically, the numbers in front that are where a and b are can be positive, they can be negative, just as long as they're an actual constant number. So let's determine whether each of the function represents a linear function. Okay, each of these equations, is it a linear function or not? And let's determine the domain and range. So the first thing I notice when I look at this one is there's no x or y, but does that mean that it cannot be linear? Well, no. As you take a peek at that function itself, it could easily be linear. So let's look at the first one and let's explain why that this one may or may not be linear. Well, the first thing I want to do is I kind of want to be able to take it and possibly solve for one of the variables. If I can maybe solve for one of the variables and, make it in terms of the other, then I can kind of make it look very similar to that kind of setup that we're looking at. So let's look at this here. So that 0 equals 2t minus s plus 1. Now, as I'm looking here, I'm noticing it might be a little bit easier just to solve for s. So let's go ahead and solve for s. Okay, and to do that, remind yourself what we're going to do is I'm just going to add the s to the other side here. So when I say solve for it, basically it means isolate it. Okay, so it's now isolated. Now 0 plus s is still just going to be that s, and we have 2t plus 1. Okay, so if I look at that and then put my lovely formula that we were kind of judging things by a little bit here. So remember that formula was f of x equals ax plus b. It does seem to have that kind of format. Now remember I said f of x could also be written as y if we need to, so as long as it's like two separate variables like this. So we have the two variables, we have our s and we have our t, and then we have these number parts, which looks like it ends up in that beautiful formation in which we have. Okay, so taking a nice good look at that, we can definitely see that it does look like it's linear. So it is actually a linear function, and that's basically because we can take those variables. We know that they only have to the first power, and we can separate them out very nicely. And when we solved it for s, we can make it look even better. Now, as I'm looking at it there, we can also see that there's really no restrictions on what I can plug in for the variables. So there's really nothing that says I can't plug in any number. So the domain and range of both of those variables, s and t, are going to be all real numbers. Well, let's look at the second one, that y equals 5 now. Now, in that y equals 5, so let's just take a good peek at that. Y equals 5, and then let's look at y equals ax plus b. So we can see that y lines up, but there's no x here. So does that mean that it's not linear? Well, no. Think about it in terms of, well, what if I were to take that, and instead of right here, okay, I'll switch the color on it so we can kind of see it a little bit better. So let me pull that 5 way back here. Well, that 5 is positive, so 5 could be b. What is the only number that maybe I can plug in front of x that would make that x go away? Well, that would be 0. So if I say 0 times x is 0. 0 plus 5 is 5, which is where we can get that y equals 5. So it can actually be written in that format that we were talking about, that y equals ax plus b. So is this linear? Well, 100% yes. Now, let's talk about the domain and range of this. Well, in the domain, I can have anything I want because basically I can put in any number for x and it's still just going to come back out with 5, but I can plug anything in. There's no restriction on it. So the domain on this one is all real numbers. However, the range is 5. Now, you'll notice I said the range is 5. It's just one number itself because there's no other number that I'm going to get back out. Y is always going to equal 5, but x can be any number in our case here. Okay, let's look at that last one there. So that is that x times y equals 2. Now, we have a little bit harder time on this one because remember, the function that I'm looking at, so we're looking at x times y equals 2 here. And when I go back and look at my formula that I was looking at earlier was y equals a times x plus b. Now, even if I were to move the y over to the other side here, okay, like we did with that s earlier, that would just be a times x plus b minus y. They would still be two separate terms. They're kind of separated out. And in our case here, this is one big term, which means I can't really separate them unless I do some type of like division. So even if I were to do division, so let's take a peek at that. So our x times y equals 2, and let's do divide by x because I want y by itself. So if I'm going to divide by x, what I do to one side of the equation, I have to do the same thing to the other. And when I do that, I get y equals 2 over x. And again, I can't just magically make that x pop up on the side here because it's in the bottom of a fraction. I can't do that. I can't move up over the bar. So when we look at that there, it doesn't meet that requirement of what we're looking for, that y equals a times my x plus b, because this is still going to be 1 over x no matter what I do. So that's not where we're looking at here. So therefore, we do have that issue, and we can see there that it is not a function. I'm sorry. So it's not actually a linear function itself because we can't separate them out. Now, because it's not a linear function, we're not even going to attempt to find the domain of range. It said only if it was a linear function. Let's talk about finding our intercepts. Okay, now I'm going to say finding them algebraically, and I'm going to put a big old star here, ladies and gentlemen, because this is one of those things that you really need to know. Finding our intercepts is definitely going to be something that comes over and over and over as we go through the different sections. We always kind of want to know what is the x-intercept and what is the y-intercept. Now there are two intercepts. There's the x and the y, okay? And basically to find the y-intercept, you plug in the opposite letter, which would be x. So you're going to set x equal to 0 in the equation and then solve for y. Once you've done that, your final answer will be a beautiful ordered pair. Okay, now again, we just said x was 0, so what would be that y value? We'll just call it b in our case here. Okay, now for the x-intercept, same setup, except for opposite of x is y. So we're going to set y equal to 0 in our equation and then solve for x. And when you do that, you should get some point where you know the x value, but the y value you said was 0. Okay. This very basic thing, everything that I've highlighted in, kind of underlined in red, is what you kind of really want to write down and make sure that you know. A lot of the other stuff is a little bit more kind of wordy, but the basic idea is for the y-intercept, you're going to set x equal to 0, solve for y, get an ordered pair. For the x-intercept, you're going to set y equal to 0, solve for x, get an ordered pair. So let's actually do that. So we're going to find the x-intercept and the y-intercept of the graphs. So I have 4x minus 8y equals 16. And we're going to do this algebraically. We're not going to plug this in the graphing calculator. We're going to actually do it by hand. because learning this by hand right now means that later on we'll still be able to do it by hand when the problems get even harder, because the method is not going to change. So the first thing I'm going to do is I'm going to write out the fact that I said the word x-intercept and y-intercept, but if I even say the word intercepts, there's always two that I'm going to look for. So I'm going to kind of divide my paper in half here, and let's do the y-intercept first. So remember, for your y-intercept, basically what we're going to do is we're going to plug in x equals 0 into our equation. Okay, so I've plugged in x equals 0, and after we plug in x equals 0, we solve for y. Okay, so now let's solve for y. Well, let's start by 4 times 0, which is 0, and 0 minus 8y is going to give me a negative 8y there. So we have a negative 8y equals 16. So I'm going to solve by basically dividing by negative 8 there, and we get y equals negative 2. So the beautiful y-intercept is basically the order pair x equals 0, y is negative 2, and there we have it. So let's do our x-intercept now. So for our x-intercept, again, the rule is basically you're going to plug in, if this says x, opposite letter, so y equals 0. Okay, we've now done that. So it should say 4x minus 8. Instead of y, we plug in 0 equals 16. Again, you'll notice I'm kind of doing this separately. I'm not going back to what I've already done. It's literally like I have two separate problems in one. After we've done that, we're going to solve for x. Okay, so 8 times 0 is still just 0. So 4x minus 0 is still just 4x. So we get 4x equals 16. Now this is 4 times x equals 16, so I'm going to divide by 4 to figure out what I need to multiply by it to get 16, which happens to be 4, and we get that beautiful x-intercept to be 4, 0. Okay, so again, very, very important. Make sure you make really good note on this, because these are really helpful and you're going to see it come back over and over and over. Let's talk about word problems or applications. So let's talk about a business property is purchased with a promise to pay off $60,000 loan plus the $16,500 in interest on that loan by making 60 monthly payments of $1,275. Now the amount of money remaining, we'll call it Y, to be paid on that $76,500, that's basically our loan that we have plus the interest is where I get that, okay, is by reducing it by $1,275 each month. Okay, now, although the amount of money remaining will be paid changes every month, we can actually use a linear model to kind of function this. So look back at that kind of beginning part there. And as we're looking at it, so let's talk about kind of a couple of things here. We talked about how y is going to equal basically this being reduced by this each month. Now, every month that's going to change. So each month is actually a variable. So we're going to call that variable x. So we have basically 76,500 minus 1,275 times x. And we're going to let x equal the number of monthly payments that we actually made. Now, earlier in the problem, we talked about how we know that x is only going to go from 0 to 60 because we're making 60 monthly payments. So we have a limit on what x can be, but we can still take this and apply a lot of other things. And let's recognize a couple of things from it. So let's start by finding the x and y intercept. So even though this is not the same setup as the last one, because it does look a little bit different in that setup the way we have it, we can still go find that x and y intercept. So we'll start off by putting our x and y intercept up there, okay? And then we're going to work it on out, okay? So as we work it on out, make sure that we are paying attention to what we have. Now, if you want to take a moment and pause the video, you can pause, and that way you can see if you have it. Okay, so now that you've taken a second and tried to work it out, hopefully you paused the video and worked it, let's see how to do it. So remember yourselves that basically the rules of the road, again, write them down if you need to write them down until you have them memorized what you need to do. Everything I'm rating here in red is basically what I need to remind myself what to do. So x-intercept means I'm going to set y equal to 0, solve for x. Okay, so in our case here, remember that the equation itself was y equals 76,500 minus 1,275x. Okay, so now that we have that, we plugged in our 0 for a y, now we have to solve for x. Well, as I begin my solving for x, I'm going to want to make sure to isolate the term that has just x in it. So I want to isolate this term by adding it to the other side. So basically when I add it, so it's subtraction here, that's why I added it. We have 1,275x equals 76,500. Now I have that times x, so the opposite of multiplication is division. And when I divide it out, I ended up with 60. Now for my y-intercept, again, the same process, but remember, again, remind yourself of the steps if you need to. You're going to set x equal to 0 and then solve for y. Again, if you need to, I would strongly encourage you to write down these steps until you know how to do them without writing it down. And again, how do you know what to write? Well, basically when it says find the x-intercept or y-intercept, that's basically telling you what you're looking for, and that's where you have to remember the steps to do it. So for the y-intercept, I plug in x equals 0. Well, 1,275 times 0 is still 0. So basically 76,500 minus 0 is just 76,500. And the cool part about that is it's already solved. Okay, so for my x-intercept there, we have our answer is basically 60, 0. And then for my y-intercept there, we have basically our 0 for my x, comma, 76,500. Okay, now these would be the order pairs I see on the graph, but again, this was a word problem, so let's actually interpret it. Okay, so let's interpret it with the context of the problem. Now, when you think about this, as we say, interpret it with the context of the problem, remember that the x-intercept corresponds to the number of months that must be passed until we owe $0. Again, remember, x is representing the number of months paid, okay? And your y value is representing the money remaining to be paid off. Okay, so technically each one of those variables actually represented kind of a word of problems. So when I say x-intercept represented the amount that I actually needed to pay, how many months to pay, before that y value was 0, meaning I owe 0 amount. So therefore we would say it if I was to maybe write this in a little bit of a maybe a paper or something, or I'm presenting this to a company, I would be able to say, well, the loan can be paid off in 60 months. So the loan can be paid off, meaning I don't owe any money in 60 months, but I have to do 60 months before the loan is 0. Now the y-intercept is going to go with the other direction. So remember, with the y-intercept is basically the total of the loan that must be repaid after 0 months, meaning basically right after the purchase, how much do I still owe? Okay, so the y-intercept can kind of basically tell us that the total of 76,500 must be repaid in the context of this problem itself. Now, should x and y be limited in this model so that we can make sense of this application? Well, we already know that we said x was limited. So we said x itself was limited between 0 and 60, okay? So since the value of x basically has to be made in 60 months, basically we said that x has to vary between 0 and 60. However, y represented the amount of money owed. Well, the maximum amount of money that I actually owe is 76,500, which means that when I take a look at that, and I'm owing money back, I'm not going to ever owe negative money back. So I'm going to stop it at 0. Now, why am I talking about what should we limit it to? Well, this would be something that I would look at with my graphing calculator and maybe plug it in. But when I look at it, I may not be able to see everything in the calculator itself. So let's take a peek at this calculator. Now, remind yourself of what the equation itself was. The equation happened to be, when we were looking at the function, was 76,500 minus 1,075x. Oops, I need to hit the X button, sorry. There we go. Okay, so now that we have that in there, now remind yourself, if I were to just hit graph, now I've probably done something in my calculator and I may not see anything. So as you guys can see, if I hit the graph button, I really didn't see anything. So first of all, go to y equals, okay? Plug in your function. And again, for that variable x, make sure you use this button right here, this x t theta n. But when I hit graph, if I don't see anything weird, I always want to start with a basic window, which is zoom 6. This is what we call is our standard window. And we like to kind of start here. Now, this is a word problem, which meant that, remind yourself, we talked about how 0 to 60 and then basically 0 to 76,500. So what I want to do is I want to hit the window button. And with that window button, I want to go in and say, okay, the x's had to go from 0 to 60. Oops, let's go to that and clear that out. Okay, so 0 to 60. Now notice as I'm plugging them in, I'm literally hitting the number and then hitting enter and it's moving to the next thing. Now I notice on this one it says XSCL, that's the scale. We don't want to touch that, but we do want to limit our Y value. So we want our Y's to go from 0 to 76,500. Now, if I stop my Y values at this, that means it's going to be at the very, very top is my Y value. We kind of like to go a little bit above this just so we have a better idea of what it looks like. So I'm going to go a little bit above it by making it basically 80,000. So now when I do that and hit graph, I can see that beautiful graph. Again, here's where that 60 is. So if you want to go past it a little bit, you can, or above this. You can stop it off right there, but sometimes it's a little hard to see some things, which is why it's sometimes nice to go above it or just beyond it if you need to. Okay, so this is what it would look like if you have it all beautifully labeled. You'll notice here I have the scale set to represent 10, whereas in the calculator, every single one of these tick marks represents 1. If I do that nice lovely thing and hit window and change this, instead of saying X scale being 1, I change it to 10, you'll notice down here that every tick mark will now represent 10. So that's basically what that scale is. I don't recommend messing with the scale. I like to keep it as 1 unless I just really need to see something closely around that area. But these normally in your graphing calculator, we don't really mess with them that much, okay? Because in the calculator itself, we do a lot of other stuff to verify things. Okay, but when you're looking at your homework and things like that, you definitely want to kind of watch the scale to let it kind of help you answer the questions because the scales will change on the problems that you're looking at. And as you can see on the graph here, we can see that those x-intercepts, so here's my x-intercept and here's my y-intercept. We can very visibly see like where it is. It's a little bit harder to see on this one, which is why it's sometimes helpful to have that knowledge of finding it out where exactly it was. Okay, so let's talk about slope. Now, slope itself is one of those that a lot of people kind of remember from hopefully back in the day, but in case you don't, here's the formula itself. And again, make really good note of this, write it down somewhere, okay? So put this in your notes to where you want to remember it. You definitely want to remember itself. So m equals y sub 2 minus y sub 1, all divided by x sub 2 minus x sub 1. Now, this is basically to find the slope, and this is if you are given 2 points. So if you're given 2 points, you use this formula to find the slope. We use m to represent slope, and slope itself can be defined as basically the rise over the run or the vertical change over the horizontal change. Now, the little sub numbers that you see here and here on those x values are not numbers that you're multiplying by. They are literally representing which point I'm referring to. So you're given 2 points. So the little sub 1 is representing 1 point and the sub 2 is representing the other point. So you want to make sure that you're getting them from the same point when you're lining them up here. Now, we do have to be a little careful because the slope of a vertical line is going to be where you have basically an undefined slope. And so because of that, we do have to state that it is undefined because we can't divide by 0. So let's find and calculate the slope given 2 points. So let's start off by basically reminding yourself that when you're taking a peek at these, you can choose either one. It's not going to matter. Okay, so choose which one that you want to be 0.1 and which one to be 0.2. I completely recommend that if you don't have it written down and you don't really know what you're doing, I make sure that it says basically find the slope. You notice the 2 points, write down your formula itself. So that way, the more times you write down the formula, the more likely you are to remember it. Now, I do know some people use flashcards to help them remember, but I like to really write them down every time I do a problem, which also reiterates another way to help memorize it. Okay. So since this point is written first, I'm going to call this one 0.1. And since this one's written second, I'm going to call it 0.2. Again, it's not going to make a difference which one you call which. And let's plug them into the formula. So we get m equals -1. Again, it's the y value minus the other y value. And then all divided by the x value minus the other x value. Now, again, make sure that they are lining up. Okay, so make sure that this right here comes from the exact same point. It's really important to make sure on that they come from the exact same point. Okay, once you've done that, let's do the top and let's do the bottom. So on the top there, we end up with a -4, and on the bottom we have a 12. And again, all fractions must be simplified. And so in our case here, it does simplify all the way out to a -1/3. Okay, so our slope itself is just that number. There's no variable attached with slope. Slope is going to be a number itself. Okay. Now, a couple of things with slope that we want to kind of remember is basically if slope is positive, if it basically rises from left to right. So think about it, okay? One, I'm speaking in the English language here, but two, we are in the US, and so we read most of our books from left to right. So we like to actually read our graphs from left to right. So always start on the left side and put your little person or finger and on the left. And if you work from left to right, look at the direction in which you're going, okay? So my person here is moving upwards, so therefore it should be a positive slope because we're going upward. Now, my little person here is going downwards, okay, which means it's going to have a negative slope because we're going downwards. Again, always work left to right. Now, there are two other slopes that we have to think about. Now, this one here would be our nice, lovely horizontal line. So if I take my little person on the left side and walk this way, you'll notice I'm not moving up or down. I'm literally staying exactly the same. I'm constant. I'm not changing. So I'm not going up or down. I'm literally 0. Okay. So in our case here, if we have a horizontal line, the slope exactly is 0. Now, again, I'm starting at the far left here of the graph itself. Again, you'll notice I always kind of find the blue line, and that's where I'm drawing my little person. Now, as I move to the left here, what happens? I basically kind of just fall off, and now my person is basically dead, right? So in this case here, if you think about it, if you actually move left to right on this one, my person is going to fall and die. So a vertical line has a slope of undefined. Okay, it actually does not exist. We say it's undefined because when you fall off of it, you die. You're undefined. You're dead. Okay, so keep that in mind. So now let's have another formula. So the slope and y-intercept form of a line. Earlier, we talked about basically any function that is linear can be written in this y equals ax plus b, or again, I can always switch it out to say f of x. Now, that may have looked a little familiar because of the formula y equals mx plus b. Now, on this formula itself, basically, this is called the slope-intercept form. Okay, we call it the slope-intercept because you have a slope, and this number here happens to be the intercept. Now, it is very specifically which intercept. It is the y-intercept. Okay, so now when we look at this formula, we don't do a lot of plugging in. We actually use it more to identify stuff. So let's determine the slope and y-intercept of the following linear functions. Let's start with that first one there. Okay, so with the first one there, the first thing I notice is it basically is written in that y equals mx plus b format. So since it says y equals mx plus b format, I'm going to write the formula underneath it so it can help me line things up. And as I begin to look there and line things up, I'm noticing 7 is in front of that x, and then I have a minus 12, which is kind of being added or at the end there. So in our case there, I can say that my slope is 7, okay, and my y-intercept is going to be negative 12. So the slope is 7. Again, notice I did not say 7x. I just said 7 because, again, x is part of the formula. M itself is the slope. It should just be a number. Okay, and the y-intercept is negative 12. Now, I'm not writing it as an ordered pair because I said the y-intercept is negative 12. If I was just referring to that point, I would write it as an ordered pair. And again, we can make note that that will be that ordered pair 0, negative 12. Okay, so let's look at B. Now with B, we have a small issue, okay? This does not look like this beautiful formula here. So because of that, what we want to do is we want to solve for y. If we can solve it for y, we can then identify it pretty nicely straight away what it looks like. So in the process of solving for y, we're going to start by finding y first, okay? Now, as you start to find y, as we do this here, find the term that has y. So my term that has y is this one right here. Now you'll notice I took not just y, but the number that was directly in front of it and that sign, okay? Now, once you determine where it is, leave it alone. Move anything that's not in that term. So let's take that 2x and move it to the other side. Now, again, when we move terms, remember the process of moving terms is basically opposite operation. And right now there's this like invisible plus sign here. So the opposite of adding is subtracting. So I'm going to subtract it. Now, again, these are not like terms, so therefore I can't add them together. So we're just going to keep them separated. And we end up with a negative 3y equals 12 minus 2x. Okay, now that you've got the term that had y in it all by itself, we can divide by our lovely term there. So I'm going to divide by negative 3. Now, again, remember you're dividing everything by negative 3 there. Everything, left and right. Okay, once you've done that, we end up with our beautiful y equals. Now, this is 12 divided by negative 3, and this is a minus 2 divided by negative 3, and we'll throw that x out to the side. Now, any fraction should be simplified. So as you start to simplify that, you should see 12 divided by negative 3 is going to simplify down to a negative 4. And then a negative divided by a negative should help remind you that we're going to use our beautiful positive there. Okay. Now, you'll notice that when I solved this fully out here, so here it is in nice type format. It didn't matter which side you moved the y to. So if you wanted to move the y first and then add and subtract the 12, that works just as fine. Just as long as you isolate the y, it doesn't matter. Okay, so either way, if you did it the way I did it, or if you did it the way my math lab wants to do it, it's still going to come out with the answer as being basically 2/3 x minus 4. Now remember, when I wrote it, I had it as negative 4 plus 2/3 x. So I had it written this way. Doesn't really matter which way I write it. No, we do like to put the x in the front, and the reason why we like the x to be the first term is because then it lines up really nicely with the formula. And we can write that y equals mx plus b directly underneath it. However, if you wrote it this way, it's still not going to matter. You just need to be able to be sure to match up the term that has the x with the x term there. Okay, so now that we can see that, we can see very clearly what is our slope and what is our y-intercept. So in our case here, our slope is 2/3 and our y-intercept is going to be that point 0, -4, or again, the y-intercept itself is -4. What if it actually looked a little bit more like this and had a lot of words with it? So these problems here basically just gave the equation, right? This is more of a word problem style. So even if it's a word problem style, make sure that you're reading very closely any of the word problems. So the amount of money Y remaining to be paid on a loan of $60,000 with $1,650 interest is Y equals 76,500 minus 1,275X. Okay. Now, where X is the number of monthly payments that have been made, what are the slope and y-intercept of this graph? Okay, so again, as we're taking a peek at this, there's an equation in that problem. Do I really care about all this extra stuff in the problem if there's an equation? If there's an equation, I really want to make sure to highlight it. And then again, go back to the question. It says, what is the slope and y-intercept of that function? So it's making reference back to that. And that's where I'm kind of working my way through the problem. Okay. So as we look at that, you might want to write that equation in that y equals mx plus b format, which is why I said sometimes we like that x term to be written in the front. So I'm just going to take that minus 1275x and put it in the front of that 76,500. So that way it lines up a little bit better with my formula here. And again, the number in front of x is going to be my slope. And again, make sure you take the sign with it. It's very important. So this one here is a negative 1,275 is my slope. And that constant term that has no x attached to it is my y-intercept. So that b value there is 76,500. Now, we found those earlier with that 76,500 was that y-intercept. So we actually did those earlier, okay? But we can see kind of how it looked and it's able to kind of help us out. Now, the amount of money remaining on that loan itself was given by that beautiful formula, but how does the amount owed on the loan change as the months increase? So let's talk about the wording of this problem versus what we just did. How does the amount owed change as the months increase? So let's take a peek at that. We're talking about something changing, right? And remember when I said that basically slope is basically what we call a rate of change. So even if I gave it to you this way, we can kind of go, okay, the amount owed, well, that was those Y's. That was that Y thing. And the months changing as they increase is basically X. So basically it's asking me the change in Y over the change in X, which is nothing more than a fancy way of saying slope. Now you can individually work this out, okay? So you can literally go through each one of these and look this way on it and see how much is it changing every single month. Or you can basically go and look at the formula itself and we can say that the amount is changing by 1,275 a month, but it's doing it by a decreasing amount. So instead of me actually using the word negative there, you'll notice I said decreased by this amount. So decreasing by that amount is also the same thing as we see a negative 1,275 in the problem in front of X. Okay, so let's talk about the constant rate of change. So the rate of change of any linear function is that slope, okay? However, sometimes we like to call it this rate of change. So guys, you really want to make note of this word rate of change. So think of that as equating basically, if I say the word rate of change or the change in something, that is basically our slope of the problem. Okay, now in a linear function, that will be constant. So if you're looking at a linear function, your rate of change is always constant. Now, if we're not looking at a linear function, we're looking at something a little bit later on, those will have different types of slopes, and that will only be found by using calculus, and we won't get there, okay? But if you're looking at linear, linears always have a constant rate of change. So using the data of projections from 1990 through 2050, the percent of Hispanics in U.S. populations can be modeled by the following function. h of x is equal to 0.224x plus 9.01, with x equal to the number of years after 1990. What is the slope of the graph of this function? Again, the first thing I notice in this problem is they gave me an equation, okay? And I noticed that basically the question is, what is the slope? Again, keyword there, what is the slope? So do I really need to graph it all the way out? No, but I can basically take that function and tell me what the slope is. So and our slope here happens to be 0.224. Again, x is not part of the slope. X is a variable. Slope is always going to be a number, okay, when we're talking about linear functions, okay? So let's take that slope, which we just established. This was our slope, okay? And what does that slope tell us about the annual rate of change in the percent of Hispanics in the US? Okay, so this is going to involve a little bit more reading on our part. So let's take a look at what we have in the problem here. So the data projected from 1990 to 2015. Now the percent of Hispanics in the US population is given by this model. So basically h of x is the percent of Hispanics. That's the y value, right? Okay, and x equals to the number of years after 1990. So the percent of change over the number of years after 1990. So basically we can see that the percent has increased, and we say increased because this is a positive number here, by 0.224 percent points per year. Okay, let's look at another word problem because we love word problems. Okay, now a company produces and sells a smartphone with a given revenue by R of X is equal to 89.5X. And that answer will come out in dollars, and it costs by given by C of X equals 54.36X plus $6,790, where X again is the number of smartphones produced and sold. Now, what is the marginal revenue for the smartphone, and what does it mean? Okay, so new word here, marginal revenue. We haven't really talked about that. So let's talk about marginal revenue. Okay, so first of all, it said the word revenue. So there was two formulas. There was a revenue and a cost. When I say the word revenue, that means I'm only referring to this one. I don't even care about the cost one. Okay, but basically when I use the word marginal revenue, okay, so marginal revenue, again, we're only looking at this formula here. The word marginal basically tells me what is the slope of the revenue. That is literally what it says. Marginal revenue is the rate of change. So it's just a fancy way of saying, give me the slope of the revenue. So instead of saying, what is the slope of the revenue function, it says, what is the marginal revenue? Okay. So in our case here, again, I'm only looking at that revenue function here. And again, I'm looking very closely at it. And the number that would be in front of X is my slope, which is 89.5. So the marginal revenue in here is $89.50 per unit sold. Why am I saying per unit sold? Well, again, remember, what is X? X is the number of smartphones produced or sold. Now, produced would be in our cost here. Sold would be revenue, because revenue is how much money is coming in. So this basically means that the sale of each additional smartphone will result in an addition of $89.50 for extra money coming in for our revenue. Okay, so now that we've learned revenue and how to find marginal revenue, let's find the profit. So let's find a profit function. Okay. Now, this is going to have to go back a little bit, and let's remind ourselves of what exactly profit is. Okay, so profit itself, as we think about it, profit is money you make. Now, when you run a business, we have revenue, and revenue is not money I make, it's money coming in. Cost is the money used to produce something. So even though I have money coming in, so think about it, when you make a meal, that meal still costs you money, right? Because you had to buy all the products to make it. So every product you have, it costs somebody to make it, but then you sell it at a higher amount. So you have more money coming in than what it cost you to get it. So we should have a profit, right? So that right there is basically how we create our function. So to find the profit function, we basically need to take the cost function away from the revenue. So a lot of people remember it this way, that basically profit is equal to our revenue minus our cost. Now, that seems a lot to write every single time, okay? So in our case here, we might want to say P equals R minus C. Okay, so instead of me saying the word profit and revenue and cost every single time, an easier way to memorize that formula is P equals R minus C. Now, in our case here, we have a profit function, but we have to put it together first. So we'll start with our revenue function, okay? So here's our revenue function. Here's our cost function. Now, remember that cost function had multiple things in it. So we like to remind ourselves to always put parentheses around that. And then once you have parentheses around that, then you're going to take the step where you distribute it, okay? So you have 89.5x minus 54.36x, which can combine to be 35.14x. And then it's still minus 6,790. And now we have our nice, beautiful profit function. Okay, so let's make note of all of that. Okay, so that profit function that we just found, again, we took a second and actually did the math and did it. Okay, and I know I've done it for you down there, but remember, you're literally doing this math down here and you're simplifying it. Okay, let's take a peek and let's figure out the marginal profit. So instead of the problem giving me asking what is the profit function, it may have just literally said, what is, and let me change that to an easier color there, what is the marginal profit? So the word here is referring back to profit. And since I'm referring back to profit, the word, again, marginal in front of it should give me a good hint that basically this is basically the slope, right? So we want to know the slope of the profit function. Well, let's remind ourselves of what that profit function was. So the profit function that we created, we're going to call it P of X to name it there, was that 35.14x minus 6,790. That's what we just did. So that was literally, we found the profit by basically taking the revenue minus the cost. Once you've done that and simplified it, we then have this in this beautiful format here, and we can identify what is the marginal profit. In our case here, our marginal profit would be 35.14. And again, if you need to, on the bottom underneath there, remind yourself y equals mx plus b. Again, m being the slope itself. And since m is the slope, we can see that's where that 35.14. Now again, the word marginal is what is telling me that I need to go for a slope. Okay, so that was actually our nice, lovely section there. And hopefully, if you have questions, reach out to your instructor if you need a little bit of extra help with that.